to have Professor Eduardo Miranda here. Professor Miranda got his bachelor's at Universidade Federal de Minas Gerais in 1984, his master's at Universidade Estadual de Campinas, UNICAMP, in 1988, his PhD in 94 at Rutgers with Piers Coleman, and then he went for a postdoc from 94 to 97 in Tallahassee, where we met. We knew each other from Campinas. Obviously, we were there for a few years, but we met again in Tallahassee when I went there in 95. He was there from 94 to 97. And since 97, he is a professor at UNICAMP, and he has been a full professor since 2010. And today he's going to talk to us about disordered interacting electron systems, some insights from one-dimensional systems. So thank you very much, Professor Eduardo Miranda, for accepting our invitation. The microphone is yours.
Thank you, Jorge. Thanks for the invitation to be the first speaker this year. And so I'm going to talk about a problem that I consider very interesting and important in condensed matter. And I will talk about a few contributions that my group and I have made along the last several years. Very modest contributions, but I hope to be able to at least interest you in this problem. So before I start, let me tell you about some of the people involved in this work. So these are basically students, Iago and Luis. Luis has already graduated, and former student Victor Quito, who is in the US right now, and Pedro Lopez, and a collaboration with a longtime friend, José Abel Hoyos from USP. There are other people involved in the work here, but these are the main characters involved in the work that I'm going to talk about. The outline of the talk is basically the following. I'll divide it into three sections. So in the first section, I hope to give you a flavor of the disordered electron problem and tell you about what is known and what is not known about this problem, what's still a mystery. And this will serve as a motivation. And next, I will talk about the method of choice, the so-called strong disorder renormalization group, which I will use extensively. So I'll explain the method first and then show you some results. This is a fairly old by now method, and you can see some reviews about it here in these two references that I give. And finally, I will end by talking about the results themselves on transport properties of disordered chains. And please interrupt me and ask questions if you feel like it. So let me start by talking about Anderson localization. Probably most of you know about it. This is a single electron, a single state problem where you have a disordered system. So here, for instance, this is not the only one that you can formulate, but it's one of them, probably the first one that you see. You have the problem of finding eigenstates of a Hamiltonian whose diagonal elements are random variables distributed according to some random distribution P of epsilon, which I will not specify at this point, and some hopping, so some off-diagonal elements, which here I take to be uniform. We can also consider the problem of random hoppings. So this problem was essentially formulated by Anderson in 1958. And what Anderson showed in that paper is that this seemingly simple problem actually is quite complicated. In general, if you have a band of states in an infinite system, you're going to have a region of extended states. In other words, states which have support all over the lattice. So this on the right hand side here, you see basically the square of the wave function and you see that it's different from using colors to make the visualization better. And you can see that it's different from 0 basically everywhere. But you can also have states at the borders of the region where you have the states, and these states are going to be localized. So the wave function has support only in a small region of space, and it doesn't extend through the whole system. Okay, and of course the idea formulated by Anderson was that if the Fermi level, if you consider fermions, for instance, and you fill up these levels up to a Fermi level, if the Fermi level falls in this extended state region, you're going to have a metal, a disordered metal. On the other hand, if it falls in the localized state region, this is going to be an insulator. And if you imagine that you can somehow tune the number of electrons across this boundary here, you're going to have a metal insulator transition. Okay. Now, this problem is already very old and very extensively studied, and a lot is known about it. And I call your attention to the fact that it's a non-interacting problem. It's a problem that concerns the eigenstates of the system. So let me tell you what is basically the most important facts that are known about this. And so since work by Mott in the 60s, it's known that in one dimension, one spatial dimension, any amount of disorder will lead to localization of all the states. In 1979, this very important paper, so-called Gangle 4 paper, established, this is a picture from that paper, it established that this is true also in 2 dimensions. Okay, any amount of disorder will localize the system in 2 dimensions. I'm talking about generic disordered systems. There are special cases which are not generic, where this is not true. So this is generic problem of localization. And in 3 dimensions, you do have a transition. And so in other words, if you look at one specific energy of your spectrum, if you increase the amount of disorder, the state at that energy will go from being extended to localized at a critical disorder strength. Okay, so this is known, has been known for a long time. Now, let me tell you about experiments. So perhaps the most important experiments that were done to address the localization problem are experiments on doped semiconductors. So this is basically silicon that's been doped with some donor or acceptors like phosphorus and boron. And these will be randomly placed impurities in the silicon lattice. Here in this picture, phosphorus impurities. And what people found out when they did experiments on these systems, as they varied the concentration of impurities, they found out that when the concentration is large, like in this case here, basically you can say that the wave function will spread out through the impurity sites, and you have extended state, and you have a metal. So this is the situation for n bigger than nc. But if you decrease now the amount of impurities, there comes a time when the conductivity, this is the conductivity at 0 temperature, plotted as a function of the density of impurities. So if you decrease the concentration of impurities, there comes a time when the conductivity goes to 0. You have a second order continuous phase transition at 0 temperature. So this is a quantum phase transition between an insulator and a metal, or a metal and an insulator. And because it's a second order phase transition, you can characterize its critical exponents. And for instance, the exponent of the conductivity called mu here, it has a value around a half in the so-called uncompensated samples, where you just dope with phosphorus, for instance, or in the compensated samples where you dope both with phosphorus and boron, this exponent is around 1. Now, this, as I said, the theoretical problem had been studied for a long time. So basically, you can calculate this exponent with extremely high accuracy numerically. And what you find is that the exponent is 1.757. So very different from these exponents that are found in nature. What's even more interesting, a very powerful approach to this problem, so-called nonlinear sigma model approach, has been pursued also extensively. And the state-of-the-art calculations by Hikami, which go up to 5 loops in perturbation theory, give you an exponent which cannot reach the numerical value. So in other words, the best perturbation theory results based on the nonlinear sigma models are still very far from the numerical results, which are basically considered to be exact. And this exact value here is far from the experimentally determined value. So we have a problem here, right? And what most people will tell you is that perhaps what's lacking in this description is the interactions among the electrons, which were completely neglected in that model that I talked about. Furthermore, you can look at the spin response of the system. So, for instance, if you look at spin susceptibility and the specific heat coefficient as a function of temperature, you find that it's basically given by a strange power law with an exponent alpha that's around this value. So, in other words, it's a divergent susceptibility. And what's more, this divergence is seen both in the insulator, where you expect perhaps to see divergence because you can imagine that in the insulator you're going to have localized electrons. These will give rise to spins. These spins will be essentially free and will give you a divergent susceptibility. But this is also seen in the metallic phase. So these are plots of the susceptibility across the metal insulator transition. And you basically see that the response is very similar in both phases. Okay, so you can have a tentative phase diagram like this one here, where you have the metal insulator transition that I talked about at a certain point of disorder. You have an insulator to the right and a metal to the left, but in a region close to the transition, already in the metallic phase, you also have some sort of non-Fermi liquid behavior that's characterized, for instance, by the spin response or this specific heat. So, you basically have no hope of understanding this without interactions in this problem. So, so the lesson here is that, okay, the Anderson localization problem is well posed and well understood, but the phenomenology, when you try to apply it to real systems, is not consistent with ignoring interactions. And this is basically an open problem. A second conundrum that I want to show you now is experiments done on 2D systems, two-dimensional systems, where you do not expect to see a metal insulator transition according to the non-interacting theory. So these are experiments done in MOSFETs first and then heterostructures. These have been reproduced in many different systems by different groups. And what you see is a clear indication of a metal insulator transition. So this is the resistivity as a function of temperature for various amounts of impurities in 2 dimensions. And you see that as the concentration is decreased, the system clearly goes from an insulating phase to a metallic phase. Now, what's also interesting about this system is that these are semiconductors. You basically know everything about semiconductors. So you can very accurately estimate the average kinetic energy and the average Coulomb interactions among electrons. And you are in this rough estimate, you get that interactions are around 10 times as strong as the kinetic energy, suggesting that perhaps this behavior is due to interactions once again. Okay, so this is the problem we are facing. So we know a lot about the distorted problem without interactions, but there are many mysteries when you have to consider interactions. Now, there are theories about that try to incorporate interactions, for instance, in the nonlinear sigma model description I talked about. I'm not going to talk about them. Basically, I would say that except in the perturbative regime, they are also not able to explain all these features that we see here. And they have problems of their own. So what I'm going to talk about now is a different method, a different theoretical method to address this problem, which is called the strong disorder renormalization group. This is a fairly old by now method, and it's very powerful in one dimension. And I think 99% of what I'm going to show you is in one dimension. But it has the advantage that it can treat the interacting problem with a reliable tool, as I will try to convince you right now. Okay, any questions at this point?
Maybe yeah, sorry. Just because you said that, I mean, the sigma model also predicts the critical exponent like to be less than 1/2 of what is numerically found, right? So I mean, that's even a problem without interactions, right?
That's right. That's right. That's what I was trying to show you here, right?
Yes. Okay. And so can you comment further on it? And then the question would be, do you have also prediction from strong disorder renormalization group for this?
No, no.
Like, okay.
For interactions or without interactions?
Without interactions, like just
yes, I will show you results about that.
Okay.
I will show you results about that. So
and is this
here,
closer to numerical or is?
Oh, it's fairly accurate. I will show you in many dimensions actually. So so what I can comment about this is that I consider this to be a huge failure of the nonlinear sigma model, right? So this is a 5-loop calculation. It does not even come close to this. And it's a funny story because below 5 loops, there's basically no corrections to this exponent, and it is equal to 1. So you have to go to 5 loops to get the first correction to 1, which is found at the first loop calculation. And after the amount
and it goes in the wrong direction, right?
And it goes in the wrong direction. That's right. So this is a huge failure. Right. So, and once again, this is for the non-interacting problem, right? So, and I will show you that I have a paper on calculation of this exponent for the non-interacting problem with the renormalization group, and it's quite okay.
Okay. Thanks.
Okay. So, so the method. Right. So I will illustrate the method with this sort of paradigmatic problem here, the random Heisenberg chain. But I must say that this can be used in different contexts, different systems, as I will actually talk about later. Okay. So think about this Heisenberg model, spin-a-half Heisenberg model with random antiferromagnetic interactions. So I'm considering random J's, but they're all positive. Later on, I will talk about the case when this can be also negative. But at first, let me talk about the positive antiferromagnetic case. So J is going to be a random variable distributed according to some distribution, which I left unspecified. And the distribution has a higher energy cutoff, which I call omega here, and it's going to be important for us later. So the method is quite simple. It's a sort of a spatial renormalization group method, and it goes as follows. So you imagine you have a realization of a disordered Heisenberg chain, and you look for the largest coupling in your system, which I call omega here because it's probably close to the cutoff omega of the distribution. So these two spins, which I call S2 and S3 here, are strongly coupled by omega. And the local level structure is a singlet, in other words, spin 0 configuration, separated by a gap of omega from an excited triplet state above. Okay? So if you're interested in low energies, you can basically forget about this triplet and you can substitute a singlet state for this pair of strongly coupled spins. Okay? So you basically, since a singlet is basically something that has no structure, you can think that you just cross off this strongly coupled pair. But you have to go further now and analyze what the coupling of this strongly coupled pair to the other spins does to your system. So you can do that in perturbation theory, and you can show fairly easily that the adjacent spins, which are called S1 and S4 here, are coupled through, as I said, second order perturbation theory by a coupling constant J tilde, which is given by this formula here. And as you can see, J tilde is smaller than both J1 and J3, and also, of course, smaller than omega, which is the cutoff. So in other words, you eliminated a strongly coupled pair, and you recoupled the adjacent spins with a renormalized coupling J tilde. So the net result, as I said, is this is just what I said. In one dimension, the topology of the chain is preserved by this decimation step. This is not true in higher dimensions, but in one dimension, this is true. So the idea now is you iterate. So you go for the next largest coupling, and you do the same, and you do the same, and so on and so forth. Okay, so pictorially, what you have is the following. You look for the strongest coupling, you cut it off, renormalize across it. Do it for the next one, next one, next one. And then all of a sudden, after you do this many times, you're going to have to renormalize bonds that had been renormalized before. So it's going to be a bond that's longer than the initial bonds that you decimated already, okay? And then you're going to do it to even larger bonds like this one here. And if you imagine that you do this down to the ground state energy, to the lowest energy of your system, you're going to have a ground state, which is basically a collection of random singlets, as they are called, whose positions are completely random, and most importantly, whose sizes are also of all possible values, right? Because you can have small ones, the ones that are decimated first, then slightly larger ones later on during the flow, and then larger and larger ones. Okay, so this is called a random singlet phase or valence bond glass. Okay, so the picture, at least of the ground state, is clear, right? You can talk about the excited states. The excited states are going to be just basically broken bonds. As you, for instance, increase the temperature, you break the largest bonds, because the largest bonds are going to be the most weakly coupled ones. So you're going to break them first. And you can also use that knowledge to make predictions about physical quantities. I'm not going to go into many details of all these things you can do with the method here. I have a lot of things to talk about, so I concentrated on the most important ones. But you can ask me later if you want. And another important result of this method, when applied to this particular system, right? Other systems may be different, but this particular system is universality. So as I showed before, the renormalized couplings are smaller than both J1 and J3, and of course, then omega, which are the three couplings that you removed from your system. So pictorially, you remove strong couplings and you introduce back renormalized weak couplings, right? So this is a real numerical simulation for a Heisenberg chain. And you can see that the tendency of this picture here is to generate a large weight of the distribution of couplings at low values of J, right? So that it's clearly seen in this animation here. So what can be shown, and was shown by the pioneers of the method, is that a large class of distribution, basically all of them, for this particular problem here, the Heisenberg chain, are attracted by the SDRG flow to a distribution that's almost a power law, except for the fact that the power of the exponent of the power law is also flowing with as you decrease the cutoff omega. So as you eliminate bonds here, your cutoff is going to be decreasing, and as it decreases, this log will diverge and the alpha goes to zero. And you see that as alpha goes to zero, this distribution tends to a distribution of the form 1 over j, which is not normalizable. Okay, so what this means is that if you try to have a measure of the disorder strength of your system, which can be made into this ratio of the standard deviation of the couplings divided by the mean, you can easily show that with this distribution, this ratio goes to infinity. In other words, the effective disorder of the system increases without limit. So this is what we call an infinite disorder fixed point that you flow towards as you iterate the system. Okay, and the interesting thing is the following: because the flow takes you to an infinitely disordered system, the second order perturbation theory that you did at the beginning becomes essentially exact asymptotically. So when you were at the beginning, you're doing second order perturbation theory, you're making some mistakes, but those mistakes, the errors in those decimations is going down as you lower the cutoff, and the method is asymptotically exact. You can actually deduce some exact results from this picture that I showed here. Okay. Okay. Among the many physical quantities that you can calculate with this method, I will concentrate on the spin-spin correlation function at t equal to 0. Okay, and for reasons which will become clear later. So this is the picture of the ground state. So this is t equal to 0. The ground state is this random singlet phase. Now, if you try to calculate the average spin correlation functions between spins that are distant by a distance r, you see the following. If the pair that you use to calculate the average is this pair in the figure here, these two spins, they belong to different singlets. So they are very weakly correlated. Basically, the expectation value here is 0. There's no correlations among these spins. You're going to get 0 for this pair of spins. If you slide this down, and for instance, you take this with this, they are also in different pairs, and the correlation function is going to be very small also. But and you can actually show from this, okay, but actually you have to go beyond perturbation theory to show this. You can show that the typical value of the correlation function, in other words, if you take the typical pair of spins, the typical pair of spins will not belong to the same singlet. They will belong to different singlets. And the correlation function is going to be very, very small. And you can show that it decays actually as a stretched exponential with an exponent, which is one of the important exponents of the method, which in this case here is 1/2. So this is a typical pair and the typical correlation function. Now, if you happen to come onto a pair of spins which do belong to the same singlet, then of course the correlations are going to be very strong. They are forming a singlet in the ground state. The correlations will be over order 1, and this is going to be a very strong correlation. So what happens is the following. The average value is dominated by these rare cases where the two spins fall in the same singlet. But the typical value will be close to 0. And you can basically use this reasoning to calculate the average value of the correlation function, which is different from the typical value. And the average value actually decays as a power law. It has, of course, the usual sign dependence of an antiferromagnetic system, but it decays as a power law with exponent 2. So you see that you have very different behavior when you look at typical and average quantities, in this case, the correlation function. And the reason behind this is the fact that this particular quantity here is distributed, it's a random quantity, and it's distributed with a very, very, very wide and anomalous distribution, which I tried to plot here, such that the typical value is very small, it's around here, but the average value is around here, okay? So I quote here work not by me, but my collaborator, José Arroyos, where he calculated the distribution, the form of this distribution, which had not been calculated before. It's a very, very nice work that he did recently, and completely consistent with this picture that I'm talking about here. Okay, a very wide distribution. So the lesson to take home from this is that there are some quantities in disordered systems such that the average value is no tool if you want to look at a certain physical quantity. Sometimes the typical value is what's really necessary. We have the tendency to calculate averages without thinking too much about it, and it's a dangerous proposition, okay? Okay, so Tobias asked about the non-interacting problem. We did use the SDRG to treat this problem. This is actually this had been done actually, Tobias, before by I think by Ando in the 70s, where you can imagine that you have a disordered system like this, and for instance, if you look at the largest values of these quantities here, you can imagine that T is also distributed, also disordered, and you have, if the largest value is a hopping, then you can imagine that these two sites here form a bonding and anti-bonding states, and you can eliminate the anti-bonding state, which is high energy. And as you do that, you renormalize the hopping between the remaining sites and also the energies of the remaining sites. You do this with perturbation theories, and you get these formulas here. And if the site energy is the largest coupling in your problem, you can do something very similar and also renormalize the other quantities and study the flow of the epsilon and T distribution, right? And I call your attention to the fact that even if T is not initially disordered, random variable, because of these renormalizations, it very soon will become random as well, okay? So we did this for these systems and calculated, for instance, the conductance of the system. And you can see, for instance, this is the three-dimensional case as a function of disorder. You see the two branches, the conductance going to 0 in the metal, going to infinity in the insulator, as a function of the size of the system, okay? And we could calculate the critical exponent in this case up to dimension 10 and compare with various, for instance, the Slavin state-of-the-art numerical calculations of these exponents. This is was a different proposal for the behavioral exponents above 3 dimensions. And our predictions are these black circles here. And basically, this was trying to distinguish between various proposals for how this exponent behaves as you increase the dimensions. Okay, so this can be done. As I said, okay, you can dress this up as SDRG, but this method of decimation is quite old. It's not by us, and even before the SDRG was invented. So, so this is still non-interacting problem, but now let's look at an interacting problem. Okay, so you have to use some tool to describe your system, and the fact is that you can adapt the method to calculate correlation functions, and for instance, in this case, you can use you can use the SDRG to calculate a current correlation function, which will give you the conductivity of your system according to the Kubo formula. So I'm going to formulate this question in terms of spins, but as I will show in a moment, you can think about interacting fermions in the same language as well. Okay, so if you look at the spin problem, the Heisenberg problem, for instance, you can define a spin current operator, which is very easily shown to be given by this S plus S minus between two sides. Basically, what this is doing is taking a spin flip from one side and moving it to the next. This is why this is the spin current operator. And you can use this in a Kubo formula. This is the Kubo formula at 0 temperature for the conductivity as a function of frequency, using the lemma representation, but this is not very important, okay? So what you can see, the important elements here are the current operator, the total current operator. This is the ground state. These are all the excited states. And this is the energy of excitation, the difference between the energy of state n to the ground state. So you can use the SDRG to calculate this quantity. Basically, what you have to do is you have to follow the renormalization of your operators as well, right? As you crank up the RG routine, the current operator will be renormalized. As you can see here also, and as was obvious from the beginning, the sizes of the bonds also become different. So for instance, this new size here is the sum of this L1, L2, L3, right? And there's a new operator, a new spin current operator for the decimated pair. And then you can basically, if you want to calculate the conductivity at scale omega, omega now being the little omega here, the frequency at which you're calculating the conductivity, what you have to do, you run your RG until your energy scale becomes equal to little omega. So large omega becomes equal to little omega. And then you can calculate this formula by applying, basically looking at the energies of excitations at that scale, which are basically going to be the next bonds to be decimated. And you have to calculate the expectation value of the current operator. In this case, the renormalized current operator after the.
Eduardo.
Yes.
Just a quick question.
Yes.
I understand that the strong disorder G work very well for the ground state. Here is not clear because if you doing dynamic, you also need the excited state. I don't know how you know that is really work for.
Sure, it's not only for the ground state. It's certainly for the low energy sector, but not only for the ground state. Okay, so basically, once you are very close to, I'm not going back to the plot, but once you renormalize the P of J distribution, and it becomes close to that universal distribution that you have, that Daniel Fisher and other people derived many years ago, then even for the low-lying excited states, the SDRG will give you a good description of those states. So basically what I'm saying is the following: if this little omega here is small, is for low energies, then you should be safe. Okay.
Okay.
And there are actually this method has been adapted to many situations, as you know, right? Because we have a paper together on this kind of thing. But it has been adapted also for any energy of the spectrum. Okay, you can't try to use it in that case. It's harder, of course, to use it. It's much more expensive to do it. But you can do it in principle. It hasn't been fully explored, but in principle, you could do it for all energies as well. Okay. But here I'm talking about low energies. So, okay, so these people actually did this for this problem. And here I'm going to modify slightly the problem. Instead of talking about the Heisenberg model, I'm going to talk about the XXZ model, in which case the XX, XX, and YY couplings are not equal to the SZ couplings. So I put them different here, but basically it's not very different from the Heisenberg model. And they found that the system behaves like a metal. Okay. In other words, they found the average conductivity. They calculated the average conductivity. It diverges as little omega goes to zero. It diverges logarithmically to infinity. So they said, okay, this is the case of a random one-dimensional system that's metallic. Okay. Now, this is very, very odd, because this problem for spin a half, it can be mapped using the famous Jordan-Wigner mapping onto fermions, spinless fermions in 1D, and the delta interaction between SZ components is actually equivalent to interactions among the electrons. So you can map this problem. It's exactly the same problem. The XXZ spin problem is completely equivalent to a fermion problem, a fermion disordered interacting problem. And what's more, if you take the delta equal to zero limit, this is a disordered fermion non-interacting problem, which we're supposed to know everything about, right? And this system in particular is known to be localized, is known to be an insulator, an Anderson insulator, since the 70s. Okay, it's slightly anomalous. So instead of the wave function is localized not with an exponential, as is usually the case, but as a stretched exponential. There's a square root in the exponent, but it is localized. And these guys say that this is a metal. So what's wrong? What's going on? And of course, the problem here is the one that I talked about before. You cannot use average quantities when the distributions are large. And conductance distributions and conductivity distributions in one dimensions are known also to be very broad, such that, for instance, the average conductance is much larger than the typical conductance. Okay, and one way to calculate typical quantities, a very convenient way to calculate typical quantities, is through the so-called the average of the log and the exponential of the average of the log. This is the geometric average. The term suddenly blanked out completely. This is the geometric average of G as opposed to the arithmetic average of the conductors. And these are very different quantities at DC, in the C limit. Okay, so it's reasonable to expect that in the AC limit, when the frequency is different from zero, this will also be the case. So as I said, the previous metallic behavior was found for the average conductivity. And then what we did was to look at the distribution of the conductivity, and it's very, very broad. Okay, so these are distributions of the log of the conductivity. So this is log scale for various values of the frequency omega, little omega. Note here that I will often use gamma of omega, which is log of 1 over omega, instead of omega itself, because this is easier for me. For this particular system, this is a more convenient variable. So you can see here, for instance, that if you look at the lowest energy here, which corresponds to the largest gamma, which I take to be this last one here, is the brown curve that's here, the broadest one. The typical value is right around the peak of the distribution, but the average value is much, much, much larger. Okay, so this is consistent with the very broad distribution of frequency-dependent conductivity. And in fact, when you calculate as a function of frequency now, the average and the typical value, which we took to be the geometric average, the average indeed seems to, okay, so don't look beyond this peak here. This is finite size effect. Okay, so this peak will go away in the thermodynamic limit, but below the peak you have this log behavior that was predicted before for the average conductivity, whereas the typical one goes to zero as the size of the system increases. So this is consistent with metallic behavior as we expected for the system. If you be careful about what quantity you calculate for the conductivity. Now, the interesting thing is that this is also valid away from the non-interacting limit, because the RG doesn't care about interactions. The RG is completely capable of handling interactions. This delta here can be different from zero, and you get the same result. And actually, we did this for spin one chain, and also different phases of the spin one chain, and this behavior is also there as well. The average value is metallic, but the typical value is insulated. Okay. We also check. Okay. So we also double check this against exact diagonalization of the XX chain, the non-interacting chain, and this is perfectly compatible with the SDRG. Okay. So this is sort of a sanity check for us, because maybe the SDRG is not doing a good job, but you see that it's pretty much what you get doing exact diagonalization, when exact diagonalization is possible, which is this case here. Now, this can be, I'm running out of time, so I think I'm gonna skip here, give you only the highlights of this part, but you can do the same thing for the thermal conductivity of the chain. Of course, energy is also conserved in the system. Therefore, you can define a conductivity for the energy, which is called the thermal conductivity. I'm not going to go into much detail here, but you can do the same Kubo formula for the thermal conductivity. You can use it here. You can renormalize the thermal current operator in the same way. And interestingly, in the case of the thermal conductivity, there is no doubt the system is insulating, right? So here you have the plot of the average and the typical as a function of, once again, of gamma. In other words, low energies is increasing gamma. So as gamma increases, both the average and the typical thermal conductivity go to zero. So it's certainly an insulating system. And the distributions, the reason why average and typical are so close to each other is because the distributions are not very broad in this case. Okay, so the thermal conductivity does not suffer from that weird behavior that you saw in the spin conductivity or the electroconductivity. As we saw, you can talk about spins or electrons interchangeably. Okay. Now, an interesting question is the following, of course. Can you stabilize, can you have a metallic system in a one-dimensional disordered system that's stabilized by interactions? Okay, so that's the challenge in a sense, right? So for that, let's consider the problem that I talked about at the beginning. Instead of dealing only with positive J's, consider the possibility that the J's can be both ferromagnetic or anti-ferromagnetic couplings. Okay, so you can do the same game again. This was done way back by many people of doing the same kind of decimation, look for the largest coupling, and do the same method again. Now, here's the following. The difference here is the following. If J2 is positive, and if these two spins are the same, and the reason why I'm saying that is that I will show you that with the RG, the sizes of the spins will change. So the general case you have to consider is if this spin is not the same size as this one here. At the beginning, they may be all spin a half, right? But as you crank up the RG, this spin might not be a spin a half, might be a spin 1, and this is a spin 3 halves, for instance. So if the two spins are the same and J2 is positive, they will couple into a singlet. Okay, so this is the same as before, right? Equal spins coupled anti-ferromagnetically. The two-spin problem, the ground state is a singlet, right? So basically, it's the same thing. The renormalized coupling now between 1 and 4 is slightly different, but it's not too different, right? Now, if J2 is negative, or if the spin 2 is different in size of spin 3, then the ground state is not a singlet, right? So, for instance, suppose this is spin a half, this is spin 1, and J2 is positive. If you couple spin a half to spin 1 with anti-ferromagnetic interaction, you get spin a half. And if you couple them ferromagnetically, you get spin 3 halves, right? So in both cases, you have a degree of freedom here, which is non-trivial. It's not a singlet anymore. And you can do the same. So in other words, you can replace the pair of spins that you had by an effective spin, which I call the S tilde here. You can find the renormalized couplings here, J1 tilde, J3 tilde. They're going to be proportional to the old couplings, J1 and J2. And there's a formula for this renormalization here. So the lesson here is the following. First of all, you generate higher spins, right? And of course, since this is proportional to J1, this already happens at first order in perturbation theory. Here you have to go to second order. This is the first non-trivial order in this case above. But the case below, the first order is already different from 0. Now, because you generate higher spins, the sizes of the spins will increase without limit. You're going to have spins of all different sizes in the system. And you can actually show that the size of this total spin of the chain, it increases with square root of the size of the chain. Basically, this square root of L here is because this is a random walk in spin space. Okay, just like in the random walk you go with the square root. Here, the spin size goes like the variance of the random walk, and this goes like a square root of L. You can get the thermodynamics. The spin susceptibility is Curie-like, 1 over T, and the specific heat is a power law. It has a log correction to a power law with an exponent Z, which is non-universal in general, but for weak disorder, it acquires a universal value, which is 2.27. Okay, so these are the highlights of this chain with both ferromagnetic and antiferromagnetic behavior. So what we asked ourselves was, what is the conductivity behavior in this case? The spin conductivity or the fermion conductivity, if you think about the Jordan-Wigner fermions. And the reason why we asked this question is the following. Because of the growth of the spin size, they grow because basically the spins form large clusters as they get decimated by the procedure. Right? And because they form large clusters, they are strongly correlated, and perhaps this will lead to metallic behavior. This was the working hypothesis as we started this problem. Now, if you map this onto fermions through Jordan-Wigner, this problem is a very kind of interesting problem because it's fermions with some random hopping and with some interaction which fluctuates in sign, right? So before this was always a repulsive interaction, but now this can be both repulsive or attractive interactions, right? So this is sort of a system that has some tendency to become a superconductor, okay? So when you do that, you do the same procedure for the calculation of the spin conductivity, and you find that indeed the average conductivity is metallic. Now it's a power law, it's not a log anymore, right? So it diverges with the frequency, and here are the average conductivity on a log-log plot for different sizes, system sizes. And here is the typical conductivity compared to the average conductivity. So let's see here. The average one is the black one, and the typical one are the other two. This is for using different types of delta functions. You remember the Kubo formula has a delta function. You have to somehow give some broadening to that delta function in order to calculate the typical value. And whether you use one type of broadening or the other, you get different behavior. But in every case here, you can clearly see that the tendency of average and typical behavior is the same. They both increase. As always, when it goes down here, this is a finite size effect. It has to do with the finite size of the system. Okay, and when you look at the distribution, it does broaden, right, as you decrease this frequency. But average and typical have the same trend. They both go up, right? Which is why you can safely say that the system is metallic. Okay, so we have here a system which is disordered in one dimension, has in terms of fermions, is interacting fermions with random signs, right? Random signs, positive and negative, and this leads to metallic behavior. Okay. Okay, so I think I'm reasonably on time, so I come to the conclusions. So first, the main message I would think about this problem is I try to convince you that the disordered interacting electron problem is still an open problem. Okay, there are many questions that are not understood about interacting electrons in a disordered environment. It's very important to have insights from a reliable method. As I showed before, the sigma model for the non-interacting case does not do a good job for the transition. In the perturbative region, it's okay, but at the transition, it's not a good starting point. It's basically a perturbation theory that has a very small radius of convergence. So it's useful to look at other methods, and especially methods that have the potential to be generalizable to interacting problems. So I tried to show to you that the SDRG is such a method, especially in 1D. Of course, in higher D, it's more complicated, And I also emphasize that you have to be very careful when you have physical quantities that you don't know if they are broadly distributed or not. And then when they are, very often the average behavior is not indicative of typical behavior, which is the one that you should look at, usually. And I showed you one case, at least, where you have metallic behavior in 1D. And of course, the outstanding problem, which I barely touched here, is higher dimensional interacting systems. As I said, I think the SDRG has potential here, but it's not trivial. It's not obvious. It's not, in few words, the decimation step will generate many different terms, not only a few terms. And it can become very hard to follow the various terms of your Hamiltonian. So it's not trivial to go from 1D to higher D, okay? But hopefully this will be done in the future. Okay, with that, I end my talk.
Thank you, Eduardo. Thank you very much for the very interesting talk. This is open for questions. Any questions? Anyone wrote anything, or anyone who wants to open the microphone and ask her question? Edson?
Actually, thank you very much for your nice talk. George, thank you for giving me the opportunity, but apparently Rafael Costa has his hand.
Rafael Costa. Yeah.
He has priority.
Do you have a microphone? Yeah.
Yeah. Yeah. Thanks. Thanks, Professor Miranda, for the talk. I had trouble understanding how did the spin gets renormalized in that case. In the last one you showed, is because of the Kubo formula, right?
No.
It's not.
This is independent of the Kubo formula. This is just a decimation procedure that I outlined at the
You start with, let's say, spin half everyone, right, and then you decimate. So right.
Suppose that the J you're looking at, the largest J is negative. You couple two spins a half, you get the spin 1.
Yeah, right? Or 0, okay. Yeah, but in that case, it's negative. Okay.
But when J is negative, and I'm talking about the case where J can be both negative and positive, it becomes spin 1. Now that spin 1, when it couples to the neighboring spin a half, if J is once again negative, gives you 3 halves. Actually, the distribution becomes very broad, very fast. And processes like this one here that generate singlets are increasingly more rare. And you can basically, later in the flow, you can forget about this. This never happens anymore. What happens is this one. You're completely dominated by this sort of spin-forming decimation.
Mm-hmm. And just one more thing. Now it's a bit of a stretch. Can we say something about finite temperatures and higher dimensions here? Because this is a really interesting emergence of conductivity in a disordered system. And I think it's really natural to ask if some analogous mechanism is behind high temperature superconductors. That is a bit of a stretch.
It is. You see, as I emphasize here, this is a one-dimensional system with both repulsive and attractive interactions. Okay, if it had just attractive interactions, if it's in higher D, this is a superconductor, right? In 1D, there's no superconductor, but you have superconducting dominant correlations in 1D, right? But the interesting thing here is that this is both positive and negative. I want to emphasize that this phase is not a ferromagnetic phase. Okay, this problem has all these characteristics that I listed here, and others are not those of a ferromagnetic phase. This is a different phase. It's a large spin phase. It has a name. Yeah. Okay, and so I will not deny. In fact, I emphasize that J negative means some sort of superconducting correlations, and therefore superconductivity can outweigh disorder and lead to metallic behavior in 1D. That's the lesson here. But once again, if all J's are negative, this is just one-dimensional superconductor, what's called sometimes a Luther-Emery phase, right? But this is not that phase. This is both positive and negative interactions. So it's slightly different. But, of course, it has to be those negative values of J that give you the metallic behavior. Because when this J was positive, we saw that it was insulated, right? So you have to introduce the negative one here. Now, you asked about temperature and higher D. Temperature is easy, okay? I didn't mention too much here, but temperature is no problem at all. Actually, you can see here, right? This is thermodynamics as a function of temperature. This is obtained within this scheme. Higher D, as I said, is complicated. What is complicated about higher D? First of all, the connectivity is not the same, right? I don't have a picture here, but if you imagine that you have a pair of spins in let's say a square lattice, and those spins form a singlet, and you remove that singlet. Now, when you renormalize the adjacent interactions, you modify the connectivity of the square lattice, right? Because those two spins each one is coupled to 3 other spins. So you have interactions among 3 spins on one side and 3 spins on the other side. So it's different. As you iterate, and we did this many times. We did this for instance, for the Anderson transition problem that I mentioned before. Something very similar happens. The connectivity becomes very hard very soon. And basically all your sites are connected. Okay, you have a fully connected problem with different coupling strengths. Right. And of course the devil is in the detail, right? So those different coupling strengths, they have physics in it. You have to take that into account. But the connectivity is very large. So this is one problem. So for instance, in this problem here, which is non-interacting, that's the only problem, that you have a very large connectivity. And this can be handled numerically. That's why we did this. Numerically, you can handle the connectivity problem. That's no big deal, right? But that's not the only problem. So at the end, I mentioned that you also generate new terms in the Hamiltonian. Okay, and I played with one of the students in 1D for a different interacting problem. Let's say a Hubbard model. We looked at TJ also and so on. And you generate a whole slew of new terms. Very hard to control. Very hard to control. Not impossible. We didn't do it. We didn't manage to control them. But you have to think hard about it. It's not a problem. So the method is very powerful, very nice, very beautiful. But it's not universally applicable.
And also, in 2 dimensions, it isn't obvious to me that the dimmer is your fundamental cluster. I mean, you could do the RG thing with square, or it isn't obvious what is the minimum dimmer.
Yeah, people have done that even in 1D. You can, instead of taking 2 spins, you do 3. Actually, Múcio Continentino has a few papers using that scheme. Yes, there are many things you can do. I just touched on the surface of the method, okay? And in any event,
thanks.
The biggest problem is the proliferation of different terms in your Hamiltonian when you have a disordered high-dimensional interacting system. Okay, I can tell you that. It takes some thinking to do it. Okay, it's not impossible. We didn't do it yet, but it requires some deep thinking.
Thank you very much.
You're welcome.
Any more questions? I have. So yeah, go ahead. Okay. Go ahead.
And Tobias probably will ask another question too. So if Tobias don't mind, I can make my question now.
Tobias. Tobias, go first. Okay, go.
Oh, I first. Okay, sorry. No, sorry.
Oh, okay, thank you. My question is actually it's in connection with one of the questions from Rafael. So you show some finite temperature behavior, like the critical, the low temperature behavior of the system, transport property, for instance. So, and my question, how can, in connection to that, but as I said at the beginning, you are typically, let's say your approach is more reliable at low energy. You can go to higher energy excitation, but typically it's work better for low energy.
Right.
So how could you use your result to predict or to infer about thermalization of initial state that lies in the middle of the spectrum, for instance?
Right. So
can you tell anything about that?
No, not with this RG, this simple RG that I talked about here. As I said, there was a question during the talk. I don't remember who asked it, but there is a generalization of this procedure. It's called SDRG-X, which is designed to look at the full spectrum and look at questions like many-body localization and things like that, thermalization and non-thermalizing phases and so on. And but not with this method. If you want to look at anywhere in the spectrum, you have to modify. You can't. Basically, what the SDRG-X does is it doesn't throw the triplets. If you think about this case here, it doesn't throw away the initial method. It doesn't throw away the singlet. It keeps the singlet. I'm sorry. It doesn't throw away the triplet. It keeps the singlet and the triplet. And then you do the SDRG again, and then you have a different level structure. You keep it, and you go on like this. You keep everything. It's, of course, much more difficult to follow, but you can do it numerically, and people have done it. But so if you want to look at many-body localization for a large energy density in the system, you need to have the full spectrum. You need to have a method like that. Okay. Here it's for low energies.
Okay. Okay. Thank you. If you George don't mind, I have one further question, and
go ahead, please.
To you. So you mentioned a situation where you allowed the Heisenberg coupling to be negative or positive.
Right.
And I was wondering if frustrated system where you include next nearest neighbor coupling, even if both positive, so would have some sort of similar behavior.
Yeah,
or
we did that.
Far away.
Yeah. We have a paper from the time that Jose Abel was a student of mine. So this is an old paper. Not saying Jose is old, but anyway, he's not young, right? And yes, you can do that. You can do that. It's you can play with these longer range interactions. And what we showed in that paper was that many phases are known in one dimension, right? I only mentioned one, basically. Two, the large spin phase and the random singlet phase, right? But there are, basically what we showed is that at least the few types of longer range interactions that we looked at, they lead always to one of these phases. So what we showed is that basically the problem renormalizes to one of these problems here. So in other words, for instance, you put, let's call J1 and J2, right? Nearest neighbors and next nearest neighbors. So when you start the flow, you generate J3, J4, J5. In other words, longer range interactions. But then later on, they disappear. They go down to zero. You're left with J1 only. So the system, so if you put J2, you start messing up the connection, the connectivity of the lattice. It starts to grow, but then it falls back onto next nearest neighbors only in one of those classes that are known for 1D systems. So we found this numerically, and it's well documented, and I think it's pretty.
How the other couple become irrelevant perturbations, essentially, right?
They do, yeah. Not only next year, but all of them, right? At least in the regime. I'm not saying that every system is like that. I'm pretty sure that if you put long range enough interactions, you will be driven away from these phases here. But how long range it has to be, I don't know. It's a question that can, in principle, could be studied. Right.
Thank you very much. Once again, thank you for a nice talk.
Thank you.
I think that Tobias is next.
Yes. Thanks for the nice talk. Just one thing I was wondering. So if you take the 1D, let's say 1D electrons with repulsive interaction at finite temperature, you should still get some, finite conductivity, like what's variable range hopping in this, right? Or this like activated conductivity. Do you?
Yeah, go ahead.
Yeah, so you it's exponential, but in I guess 1 over temperature, but you have this finite conductivity, right?
Yes,
as finite. Yes.
Yeah.
Do you get this also from the SDRG?
We didn't do that. It's a good question. It's a perfectly well posed question.
Okay.
You have to of course think about finite temperature and DC, right? So sort of exchange the omega and T. And it's a good question. I don't have a gut feeling here. I'm pretty sure it will capture. I don't see.
Okay.
You see, because the flow is well controlled. That's where we should always start, right? The flow here is very well controlled. The flow that's basically given here by this problem, right? If you generalize to the XXZ,
right?
This is a very well understood and well under control flow. So I see no reason for this not to give you reliable answers. Although I don't know at this point what those answers are, and your question is a good question. I don't have an answer.
Yeah. And the other thing I was wondering, I don't know, because you mentioned that for the thermal conductivity, in a way, it's surprising, right? That the distribution is not broad, while for electrical. Do you have some intuitive explanation for?
Yeah, it's another very good question. I do. I don't know if it's the best explanation, but I do, which is the following. If you look at the expression of the current, the energy current is given here, you see that it depends on two constants, two adjacent bonds, couplings, J1 and J1 minus 1, right? So in other words, if you have a chain like this, it's easy to see because the energy density lives on the bonds, right? The energy density is this, it lives on the bonds. The energy current lives on the sides. It takes a bond, an energy from this bond and moves it to this other bond or to the other one, right? So it lives on 3 sides, let's say. You can center it on one side, it lives on 3 sides. It depends on 2 coupling constants, right? So what happens is the following. In general, these 2 coupling constants will be very far apart in the distribution. So one will be very large and the other one will be very small.
I see.
So in other words, the conductivity only depends, the spin current only depends on one of them. And there is a sort of the average value, there's a sort of cancellation that permits the average to blow up while the typical goes to 0. Here, because you have 2, and you can see this clearly in the analytical calculation. Even if one of them is, let's say, very large, the other one is very small, right? So because of this, there is no difference between average and yeah. So that's in a sense that's more mathematical, let's say, than physical way of thinking about the problem, right? But I don't know. The conductivity is a sort of an extent. The thermal current is not very local. It's more extended, and it's harder to get conduction from this extended object, which is the energy current in this case. And then it's just very very narrow distribution that you get. And so, for instance, this omega squared here, it's interesting. It basically when you do the Kubo formula, you have the square of this to calculate. It's the square of this guy here. So one of them gets canceled by, just like in the case of the conductivity, the spin conductivity. But the other one is left over, and is the one that gives you the omega squared behavior. In other words, the other j there gives you this. If you eliminate by hand the other j, this will blow up log also, the average, let's say, right? But here, because of the other one, it's suppressed.
I see.
It's a half mathematical, half physical answer, but that's what I got.
Mm-hmm. Great, thanks.
Okay.
Any other questions? I have a couple of questions. Is there any studies like the one you did for topological systems where you have spin orbit that endows the system with topological properties, trying to study this localization in the surface states of topological insulators, for example?
Well, there is one case which is well known, right? I think you certainly have heard about it, which is this spin one chain, right? The Haldane gap phase, right? It's a topological phase. It's a point that's embedded within a topological sector of the problem. So you can ask what happens and when you apply this method to a disordered spin one chain. So this problem has been thoroughly studied, right? And if I may come here, I'll borrow the phase diagram that I talked about for interacting electrons here. Just the line. I'm not going to talk. I'm not talking about the same system. Okay.
Okay.
So
yeah.
The point is that for the Haldane chain, you have three phases, just like this. So for sufficiently strong disorder, the Haldane chain is indistinguishable from the spin and a half case that I talked about. So for large disorder above a critical disorder strength, you have a random singlet phase. Okay, no different from the spin and a half case. Now there is another region below a certain strength here, where the system, the Haldane gap, protects the system against disorder. So in other words, this phase here before this point here is a phase where disorder is irrelevant. So
okay.
So this is completely different from the other case where it goes to infinity. Here it goes to zero, right?
Okay.
And in between, you have what's called the Griffiths phase, which is somewhat related to the large spin phase that I talked about there, in the sense that in this Griffiths phase in the middle that you have here, you have non-universal exponents that depend continuously on disorder. If you crank up the disorder, the exponent will change across this phase here, along this line across this phase, such that you still have topological order, but the system is not protected anymore by the Haldane gap. Okay, so the topological order takes longer to be killed in this Griffiths phase, but eventually it will be killed by strong enough disorder. So that's the spin one problem where you have topology. You might ask about other systems with topology, and I don't think that people have looked too much at them. But at least in this particular one, that's what happens. There is a non-trivial interplay with topology in the Haldane chain.
I was wondering the possibility. I don't know if this would be some real material. It would be hard maybe to cook this up, but a Kondo lattice with disorder in the coupling of the magnetic impurities to the conduction band. So you would have a distribution of TKs that would depend on disorder. You would have large values of TK, small values of TK, and you could start I don't know if this would make sense to say, well, the larger TKs, I take this out of the chain because they form singlets with the conduction electrons, and I keep doing that and see what I get at the end and see if this helps me to understand the heavy fermions or not. I don't know.
Right. Well, if you just talk about distributions of TK, I did this for a living for many years.
Okay.
Right?
Okay. Okay, I didn't know that. I didn't know that.
I think it's hard for you to look at that paper about distribution of TK and not be my paper. But anyway, so I explored this basically since my postdoc and a few years after my postdoc, and I beat that to death, I would say. I think there are systems, there are heavy fermion, disordered heavy fermion systems, for which this is a good starting point to look at. And I think you have good agreement with of various physical quantities with experiments in some systems. I don't think that's a whole story, but in some systems, I think that takes you a long way. Okay, we even have a paper on distribution of TKs in quasi-crystals. In other words, Kondo problem in quasi-crystals. Even though it's not disordered, it's sort of effectively disordered. And you do have a distribution of TKs there as well. This is actually not so many years ago that I had this paper, together with Eric and other people, Eric Castro. And now, and you're absolutely right to think about, some guys form strong Kondo singlets and you can sort of forget about them, and then others will be less strongly Kondo coupled and so on. The problem is there's other interactions like RKKY in this problem.
Yeah,
and
sure.
And to do both problems together, I think is one of the outstanding problems in this area. One that I have thought about a lot over the years. I have not, together with collaborators, of course, but I have not been able to address that problem in any way. But I think it is one of the outstanding problems of this area. In other words, you have Kondo problems which are governed by a distribution of TKs, but you also have spins which are governed by a J distribution like the ones I talked about here. Now, the question is to put both of them together. So I think this particular problem here is one that has to be addressed in this fashion, right? I think this is a problem where you have these two things coexisting. Kondo singlets with, let's say, RKKY singlets, random singlets as well. Now, a good description of this problem does not exist. I think it's one of the most important problems in this area. I should say. There is a paper, I should say, also by Batt and Fisher, where they consider this problem. They have some heuristic arguments, but there's no quantitative treatment of this problem. So their paper does not do this. That's the only paper that discusses this, and I believe that's a very important problem.
Okay, interesting. Then, other question, I would have just one last because I was very curious. I think on one of your initial slides where you show the Anderson results, where you have the band, this one. Why is it that the center states of the band are extended and the border states are localized? Is there an easy explanation?
Well, let's see. This is a low, usually at least, a low density of states region. So there is less, it's harder to connect to other sites when you are in this region. The reason why I have both is because the system basically has a particle, not exactly a particle symmetry, but there's an average particle symmetry in the system. So you don't expect that this end is different from that end. Right? But states in the middle are more easily connected with the rest of the lattice, so it's harder to localize them through this order. Eventually, they will localize in 3D for sufficiently enough disorder. There's a whole theory for localized states in the band tails, so-called Lifshitz tails, where you can take into account the characteristics of the tails and study localization in the tails. Okay, so it turns out that there's a tail of states here that goes exponentially to 0 here, and then you can do a reliable theory for the localized states in the tails, right?
Okay.
I guess that's it. I don't know. Maybe Tobias has a better answer than myself. I don't know.
Tobias is still there.
Yes, but yeah, I would also say, I mean, you're in the tail, so there's less states, so it's harder to hit resonances, I guess.
Okay. Okay. Thank you very much for the very nice seminar. It seems we don't have any more questions. There is no hands up. So let's thank the speaker again for the very nice talk. Thank you very much. We are starting with the right foot our semester.
Thank you, guys. It was nice.
Yeah.
It was nice.
And I will send an email to people who asked me saying that Ed